So now we're going to look at a new big theorem, Gauss's theorem. So where does this come from? But previously we saw Green's theorem, but we also saw the alternate form of Green's theorem. So we haven't used this really so much before, but remember the alternate form of Green's theorem was this. The integral over the curve of vector field f dot unit normal n ds was the double integral over the region of the divergence of f dA. So that was something that we saw before. We haven't really used as much. So, and this applied to if we're in two-dimensional R2 space, you've got a two-dimensional vector field F, and then a region R whose boundary is a one-dimensional curve C. So it turns out that we can take this version and kick it up a dimension. So how does that work? So let's just explain that for a second. So the two-dimensional region R with a one-dimensional boundary curve C will become, R becomes a filled-in three-dimensional solid, which we're going to call B, with a two-dimensional boundary surface, which as always we call S, and ds is the in parameters the infinitesimal length ds, and that becomes the parametric infinitesimal area ds. Again, we're going from little s to big S for area. And then coordinate infinitesimal area dA becomes in coordinates the infinitesimal volume dV. And then the smooth vector field F, of course, goes from having two components and two variables, it now will have three components and three variables. And so as a result, we get, just by kicking it up a dimension, we get this thing called Gauss's theorem. And it looks like this. The double integral over the surface of vector field F dot unit normal n ds equals the triple integral over B, which is going to be our three-dimensional solid, of the divergence of F dV. So we can also write this in our other notation, where we just simply say that by definition, unit normal n ds can also be written as d bold S or d oriented S. And that's just a different notation for the same thing. Other names for this theorem include the divergence theorem, for the obvious reason, or Ostrogradski's theorem, depending upon which mathematician you want to give credit to, I suppose. Okay, and there are proofs for Gauss's theorem, obviously, that are out there, and we're gonna not go through those. But instead, let's go right to an example of how Gauss's theorem works. So we're going to verify the results of Gauss's theorem for vector field F given here, and then the solid B with the boundary x squared plus y squared plus z squared equals 1 with the usual orientation. Okay. So how does that work? So first of all, in this particular question, notice that we're saying verify the results. So that means we're going to compute both integrals and check that they're equal. So let's take a look. So let's do the vector surface integral. So for the vector surface integral, also called the flux, so the flux is going to be the double integral of the surface of f dot ds, which we know in order to compute it, we'll have to do the double integral over the region of vector field f dot normal vector dA. So now we have to go ahead and find these things. So since our surface is a sphere, we know how to make the parameterization for that. So it's just r sine phi cos theta, r sine phi sine theta, comma r cos phi, right? But in particular, this sphere has radius 1, so just turn all the r's into 1, and you get this. And we know that phi goes from 0 to pi, and theta goes from 0 to 2 pi. And like we said, we already fixed r at 1 for this sphere. Okay, so there's our parameterization. Now, we've calculated the normal vector for spheres before, but we can again do it from scratch. Calculate your two tangent vectors, r phi and r theta, and you get these two vectors. Then take the cross product, and you get this thing, and then the final component simplifies, and you wind up with this: sine squared phi cos theta, sine squared phi sine theta, sine phi cos phi. And there's your normal vector. Okay, so now we can just go ahead and plug things in. So our vector field was this. Our normal vector is this. And we know that our parameters, dA, that's going to just be d phi d theta, where phi goes from 0 to pi, and theta goes from 0 to 2 pi. Okay, and now we just take the dot product and do a bunch of calculation, basically. So taking the dot product gives you this, and now we have to integrate twice. So for 2 sine squared phi cos theta, in order to do that integral d phi, we can just, here we go. So in order to do that integral, we can just d phi, we can just do a substitution, u equals sine phi, and then du will be cos phi d phi. And then on the second integral, you're integrating an odd power of sine, so you just take a sine squared and you just make it 1 minus cos squared, and you wind up with these two separate integrals. Whoa, went too far, sorry. You wind up with these two separate integrals. So the first integral, you can just integrate sine phi, no problem. And then on the second integral, u equals cos phi, and then du will be negative sine phi d phi. So doing those three integrals separately gives you this, 2/3 sine cube phi cos theta, minus cos phi sine squared theta, plus 1/3 cos cube phi with your sine squared theta. And then we plug in evaluating phi goes from 0 to pi. So doing that evaluation gives you this. And now once again, you've got something that you need to integrate with respect to theta. So let's see. Oh, we got it. Well, let's simplify first. So simplifying, you get 4/3 sine squared theta. It's a sine squared. So in order to integrate that, just use the double angle identity. And so it winds up being integrating 1 minus cos 2 theta is going to give you half minus half sine 2 theta. And then the constant in front will be 2/3. And now theta goes from 0 to 2 pi, plug it in, and you get 4 pi over 3. Okay. So doing it that way, winds up being a whole bunch. You have to do two integrals, and there was a whole bunch of calculation, as you could see. Now, let's do, using Gauss's theorem on the other side, let's do the triple integral. So, the triple integral should just be this. Oops. Okay. So, it's the triple integral over the three-dimensional solid B of the divergence of f dv. So first we need to calculate the divergence of f. So let's go back and remember what f is. So f was this right here. So the divergence of that is, well, ddx of z is 0, ddy of y is 1 and d dz of x is 0. So 0 plus 1 plus 0, the divergence is just 1. So the triple integral of 1 dv is really just the volume of the solid object. Well, our solid object was a sphere. So the volume of a sphere we know is 4/3 pi r cubed. The radius was 1, so it's just 4/3 pi. So in this case, hey, it would have been really easy just to only do the triple integral. So that's one observation. The other observation is notice, of course, that the two results are the same. Okay, another example. Again, let's verify the results of Gauss's theorem by calculating both the vector surface integral and the triple integral. So vector field F equals x squared, xy, z. And B is the solid bounded by, now I've got two equations. So z equals 4 minus x squared minus y squared, and z equals 0. So let's think a little bit about what that means. So just to take a look at the picture for 1 second. It looks like this. So it's similar to a problem that we've seen before. Notice that the biggest possible value for z is 4, and then subsequently, as you go down, bigger values of z are going to give you circles. So that gives you a rough idea of what that shape looks like. But then obviously we're saying we want it to stop at z equals 0. So let's set it up and do the calculation. So first, the triple integral. Now I'm going to do triple integral first. So we need the divergence of f. So here's f. And then ddx of x squared is 2x. Ddy of xy is x. And then ddz of z is 1. So the divergence is just the sum of those, so 3x plus 1. So now, so the triple integral, oh, here we called it e, sorry. Okay. So the triple integral over our solid, the divergence of f dv is going to be a triple integral of 3x plus 1 dv. So now we've got to figure out what are the boundaries of this solid. So looking at this, either looking at the shape or looking at the equations, what would be good coordinates to use? Because clearly we're not going to stick with, let's see, it's not easiest to stick with x, y, z. So good coordinates to use, just taking a second and noticing that the sort of boundary for x and y is going to occur where z equals 0. So at z equals 0, notice what this equation becomes. It becomes x squared plus y squared equals 4. So in order to talk about the boundaries for x and y, we're going to use polar coordinates. And z, we can just do z. So in 3 dimensions, those are cylindrical coordinates. So there you go. So in and because so the largest x squared plus y squared goes out to 4, so the radius, maximum radius is 2. So r is going to go from 0 to 2. It's all the way around. There's no restriction, so theta is going to go from 0 to 2 pi. And z, well, we've got the formula for z right here. Z goes, the bottom boundary for z is 0, and the top boundary for z is this formula right here, which we're now going to convert. And we know that x squared plus y squared is just r squared. So the upper boundary for z is just 4 minus r squared. So put that all together, and it gives you this integral. So in this case, notice that the boundaries for z are variable. So that should be your inside integral. And then r and theta can be your outer two integrals, and that could be either order. Okay. So that is after we get the basic integral, we then have to re-express it in more helpful coordinates. And of course, dv written in cylindrical, when we convert to cylindrical coordinates, it becomes r dz d or d theta. So there's that extra r there. Factor of r. Okay, so now we've got the integral. Now we just calculate. So let's see. So first, integrating with respect to z. So everything is a constant with respect to z. So it's just times z plugging in 0 and 4 minus r squared. So that just gives you r times 3r cos theta plus 1 times 4 minus r squared. So now we want to, okay, and now we want to integrate with respect to theta. Well, part of it's constant and part of it is cos theta. So integrating cos theta will be sine theta. Integrating the constant, we're just multiplying times, we're just having a plus theta. And then the r times 4 minus r squared is just a constant. Coefficients, that's just there. So now plugging in, theta goes from 0 to 2 pi. You wind up with 4r minus r cubed, and that whole business just becomes 2 pi. So 2 pi is a constant, pull it out, and now we integrate with respect to r. So you get 2r squared minus 1/4 r to the 4th, and r goes from 0 to 2. Plugging in, you get this times this, gives you 8 pi. So doing the triple integral gives you 8 pi. Now let's get back to doing Gauss's theorem on the other side. So now we have to do, I have to scroll a bit, the double integral. So notice that the double integral is going to be integral over the surfaces. Now in this case, it's a little tricky because basically there are two different surface formulas. There's the surface formula for kind of like the top cap, which is the curvy part, that's z equals 4 minus x squared minus y squared. And then there's the flat bottom, z equals 0. So we're going to have to take our surface integral and we have to break it up into two separate surfaces because that's how the formulas are. So first surface, z equals 4 minus x squared minus y squared. Okay. So to do that double integral, we know we're going to re-express the double integral over the surface f dot ds as double integral of vector field f dot normal vector n dA. Okay, so notice that your normal vector, since z is a function of x and y, it's very easy to write down what the normal vector is. It's going to be negative df dx, negative df dy, comma 1, which is going to be 2x, 2y, and 1. I need to fix this. Okay. Sorry, just fix this from my notation. Looking like that. Okay. All right. So 2x comma 2y comma 1, and then that's your normal vector, and then the vector field. The vector field was given x squared comma xy comma z, and we know we need to replace z with the given formula. So that's just going to be 4 minus x squared minus y squared. So there's your vector field. So your vector, and then we take the dot. So your vector field is right here, and now we will just take the dot product. Okay. So that gives you x squared times 2x plus xy times 2y plus 1 times 4 minus x squared minus y squared over the region dA. Okay. So multiplying that out and simplifying, you get 2x times x squared plus y squared plus 4 minus x squared plus y squared. Now the question is, what is your region? So we already know that the boundary of the region happens where z equals 0. And when z equals 0, the boundary is going to be x squared plus y squared equals 4. In other words, the boundary is a circle and the region is this filled-in disk. So if we want to do this integral, it's going to be easier to switch to polar coordinates. So let's switch to polar coordinates. So that means that dA becomes r dr d theta, and we're going to substitute x equals r cos theta, y equals r sine theta. So plugging all of that in, let's see. Oh, and then furthermore, we know that x squared, we know that r equals square root of x squared plus y squared. So x squared plus y squared is just r squared. So you wind up with 2 times r cos theta times r squared, and then plus 4 minus r squared. So you wind up with this integral, and the bounds for theta, 0 to 2 pi, wraps all the way around. And we already said the radius is 2, so r goes from 0 to 2. So here we had to convert to polar coordinates in order to do this integral. And now we go ahead and calculate. So first you've got to distribute the r, and then integrating with respect to r, that gives you, so we've got 2r to the 4th cos theta. So integrating that gives you 2/5 r to the 5 cos theta. And then you've got a 4r, integrating that gives you 2r squared. And then you've got minus r cubed, integrating that, minus 1/4 r to the 4th. Plugging in r equals 0 to 2, that gives you 64 over 5 cos theta plus 4. Integrate that with respect to theta, you get 64 over 5 sine theta plus 4 theta, and evaluate that from 0 to 2 pi, and you just get 8 pi. So doing it, let's see. Oh, and that's the first surface. We have to do the second surface. So the second surface, the formula is z equals 0. Formula for the surface is z equals 0. Now notice that because our solid was like this, the normal vector has to point outward from the solid. So for this surface, for the normal, we have to use a downward orientation. So just looking at it, z equals 0, we can use negative dx dy, negative df dy, negative df dx comma negative df dy comma 1. But since z equals 0, that just gives you 0, 0, 1. But we want the downward orientation, so 0, 0, negative 1. So there's your normal vector. But now, take the dot product with f, and recall that f was this formula right here, but we're in the space where z equals 0. So you get x squared comma y squared comma 0. Take the dot product of that with 0, 0, negative 1, and you just get 0 plus 0 plus 0. So you actually wind up with the double integral over the surface of 0 ds, and of course that's just 0. So the total double surface integral, adding those two up, is just going to be 8 pi. And so look at that. The two integrals doing either the double integral over the surface or the triple integral over the region in Gauss's theorem, you get the same answer. Okay. So now let's just use Gauss's theorem to do a calculation. So in this case, we're going to say we know one is harder, one is easier, and we're just going to convert directly. So use Gauss's theorem to calculate the vector surface integral for this vector field, where your surface S is the surface of the box bounded by x equals 0, y equals 0, z equals 0, x equals 3, y equals 2, z equals 1, with the typical orientation, which would be outward. Now notice that if you were going to do a surface integral, this is a box, there are basically 6 different surface formulas. You have to break it up into 6 different integrals. Let's not do that. Instead, let's note that the surface integral is just going to be the triple integral over the solid of the divergence of f, dv. So, and that's using Gauss's theorem. So now we calculate the divergence of f, which is right here. So you have to do ddx of the first component plus ddy of the second component plus ddz of the third component, work all of that out, and it simplifies, and you get 2xyz cubed. And now we have to figure out what are the boundaries. Well, the boundaries are super simple. They're given right there. Z goes from 0 to 1, y goes from 0 to 2, and x goes from 0 to 3. So dv is just, in this case, I chose to write it dz, dy, dx. But these are constant boundaries. You could do it in any order. And now we've got a really, really simple triple integral, and we just do it. So integrating with respect to z, you get half xyz to the fourth. Plugging in z goes from 0 to 1, you just get half xy. Now integrate with respect to y, and you get a quarter xy squared. Plugging in y goes from 0 to 2, you just get x. Integrating that with respect to x, you get half x squared. Plugging in x goes from 0 to 3, you get 4.5. So notice how we're being asked to do a vector surface integral over a closed surface because it's the boundary of a solid. Gauss's theorem gives us a way just to do this as a triple integral, and the triple integral winds up being very, very simple and straightforward. Okay. So let's talk about the meaning of Gauss's theorem. So first of all, recall what divergence means when you learned what the divergence operator does. It calculates the net flow at an individual. If you think about an individual point, it calculates the net flow at that point. So remember that if divergence equals 0 at a particular point, we say the fluid is we say in terms of fluid flow, we would say it's incompressible. If the divergence is positive, it's as if stuff is being created at that point, and we call it a source. And if the divergence is negative, we say stuff is being lost, so that point is a sink. So think of divergence as representing net flow. So in that sense, here's how we can think of what Gauss's theorem says. It says that the total net flow through the boundary is the same as the total within the solid net flow. And that's sort of broken down in this little table right here. So notice that f dot n, vector field f dot unit normal n is the flux, and that's going to give you the flow through the boundary. And of course, the double integral over the surface means we're taking all of it all together. So the net flow through the boundary is the total net flow throughout the entire solid, and that's the sum over the entire solid of the divergence, adding up at all points. So that's kind of the meaning of Gauss's theorem if we think of it overall as in the integral sense. Now there's another way to think about the meaning of Gauss's theorem if we just zoom in on a single point. Let's talk about what that means. So using Gauss's theorem, the double integral, let's come back to it. Here we go. So the double integral should be the surface. Okay. So double integral over the surface of f dot unit normal n ds is a triple integral of divergence of f dv. Okay. So now let's think about what this means at a particular point, which I'm going to call P0. So take some point P0 in my solid. So now let's shrink down. So imagine taking a small solid ball, so a solid sphere, with a radius A. So I'm going to call that B sub A. And the boundary of that is a small sphere. So that's a surface, so I'll call it S sub A. So now these things are really small, so I'm going to imagine that the value of the divergence is approximately constant on the ball. So this divergence is continuous. So what do we have? So, and ignore those little boxes, that's a formatting issue. So applying this approximation and then also Gauss's theorem. So by Gauss's theorem, we know that this is true. The double integral over my surface, my little sphere, f dot n ds, is the triple integral over my solid ball, divergence of f dv. But now we're saying my ball is so small, divergence of f is approximately a constant. So constant meaning all the same value as at that point, which I call p0. So if it's just a constant, this is just that constant times the triple integral dv. And triple integral dv, of course, is the volume. And the volume is, since it's a filled-in sphere, 4/3 pi a cubed. My radius was a. Okay, and of course, remember, all this is an approximation. It's not literally equal. Oh, sorry. That shouldn't be there. Okay. So further, if the radius is an infinitesimal, then this approximation becomes exact. So, of course, an infinitesimal, remember, is a number positive but smaller than every real number, just as a reminder. So one way to think of this is using infinitesimals. So if your sphere has this radius epsilon, then the double integral over surface integral over the surface with radius epsilon of f dot ds is just the divergence at our point p0 times the volume, where that's 4/3 pi epsilon cubed. Okay, another way to think about this, instead of using infinitesimals, is to use limits. So put all the small bits on one side, and so take the original thing and just divide. So now 1 over 4/3 pi a cubed, that's 1 over the volume, times our the surface integral, double integral over s of f dot ds equals, and sorry, the limit as a goes to 0, that is equal to the divergence at that point. Divergence of f at that point. So what that means is that the divergence is the flux, which is your double integral, and then you divide it by volume, so per unit volume. And here we're talking about the relationship, but only at a single point. So divergence is the net flow out. Flux captures that on the surface. Okay. So that's the idea. That's another way to think of what is divergence, what is flux, and what's the relationship between them. And Gauss's theorem gives you that relationship.